Good morning, good evening, and whatever time it is in wherever you are. Welcome back to the Future of Technology series. And today we're going to talk a little bit about something that everybody knows a little bit about. So much of our online experience is influenced by the astounding ability of recommender systems. Whether it is Netflix recommending movies for you, or Amazon recommending products that you should buy, the ability of recommender systems has grown exponentially in the last few years. Today, we welcome Nick Mayoraz to talk about the science and the math of recommender systems. After an education governed by his passion for math and CS, Nick started his career in academia in his home country in Switzerland. And he eventually led the machine learning group at IDEA. But then he decided to move in the industry, and so he had to trade his view of the mountains in Switzerland, in Valais, for a Silicon Valley job near Mountain View. First, he was in Motorola Labs, and then Yahoo, Quantcast, and now Google, where he serves as a research engineer. Over the past 20 years, Nick has used his machine learning expertise to improve user modeling for various personalized systems. He currently works on recommender systems and is constantly looking for ways to design new algorithms to provide recommendations that will delight the user. Welcome to our show, Nick.
Hey, thank you so much, Rita. It's a pleasure. I'm really excited of the opportunity of sharing a little bit of what we are doing at Google in the space of machine learning and more specifically recommender systems with your audience. And I hope I will be able to pique your curiosity and give you a good idea on how this system works.
Great. What are you going to talk to us about today?
So, yes, as you asked me, right, to make this presentation a little bit more personal, I will spend maybe 5 minutes telling your audience a little bit of my career path, and then I will dive right in, describe, what recommender systems are, how, what scale we are operating at Google in particular, and then I will try to give an idea of the math that is involved and how this system works at a high level, but hopefully your audience will be able to grasp the essential of it, and maybe I will, generate new passionate carriers in that field. Shall I start?
Yes.
You want me to share the screen?
Yes, let's go ahead and see your slides now.
Okay, let's go right in. So, as you said, right, I'm from Switzerland, and I'm from the south of Switzerland in the mountains, where there is really not much going on except for beautiful sceneries, ski resorts, and, a lot of tourism. So, my childhood was very quiet, except for once in a while, there would be some Indian movie maker crews coming to film the honeymoon of the next Bollywood movies. I was not exposed to much foreign activity, but I always loved math. So, from high school, and then after high school, because I really enjoyed math, I moved on to studying mathematics at EPFL. So, as you probably know, we have two IITs in Switzerland. One is the ETH in Zurich, in the German part of Switzerland, and the other one is EPFL in the French part in Lausanne. And that's where I went to, just because, I'm from the French side. And there I studied mathematics undergrad, and then I was more and more passionate about it, and I discovered the field of artificial intelligence, and in particular, neural networks. So I decided to go on and do a PhD in machine learning using neural networks. That was, long time ago. That was in the early 1990s. So neural networks were still very much in fashion at that time. So that was before that fashion died out, and of course, eventually in the late 2010, regained a lot of momentum and brought everything, back to life in AI as we see it today, and we'll get to that. But anyway, neural networks were still hot at that time, so I did my PhD in that field. And at that time, I was very passionate about academia. I saw myself as a teacher sharing my passion about mathematics and AI, and I wanted to do an academic career. So as a mandatory step to do an academic career in Switzerland, you have to go to the US. So I went to do a postdoc in New Jersey at Rutgers University for 2 years. And then I had an amazing opportunity to come back, not only just in Switzerland, but in that very home country of mine, which is this mountainous area I was describing at the beginning, where there is not even a university there, but there is this research institute in artificial intelligence called IDIAP, where actually we have quite a lot of PhD students from India nowadays. And the research is about speech processing, image processing, and machine learning. And I spent there 4 years, and I was leading the machine learning group there. And, enjoying my work a lot. I mean, that was really a unique opportunity for me to do this kind of activity at this level in this country, right? But after 4 years, I kind of grew tired of the academic life. And I thought that, I didn't want to spend the rest of my life writing papers that not a lot of people are going to read and enjoy and appreciate. So I decided to do a big leap and move on to the industry. And I had an opportunity to come here to the Silicon Valley, working for Motorola. And that was at that time, that was the peak. That was before the crash of 2000. I joined Motorola in 1999. So that was a huge company, and Motorola Labs was a very prestigious lab. And I felt very fortunate to be able to join the team of extremely smart people. I was working at that time on handwriting recognition for their tablets, their early PDAs. And after Motorola, I moved on to Yahoo, where I spent another 4 years. And there I was exposed for the first time to web data, basically, internet data, so data at a very, very large scale. So I was still doing machine learning, trying to, model all sorts of things about our users based on, the internet log data that we had. And after Yahoo, since, you cannot stay in the Silicon Valley for very long without, doing a startup experience, I joined this company called Quantcast. Maybe many of you don't know about it. It's also an internet company that basically monitor the activity online and build statistics about users going to different websites. And at that time, it was a very small company. I joined, probably were just 30 people, and now it's way more than 1,000 employees. So it's a very successful company. But after a while, I decided to go back to a larger company, and now I've been at Google for a little more over 8 years. And the past 5 years, I was in research at Google. As Prita said at the beginning, I work in machine learning, and more specifically in a team developing recommender systems, which is going to be the topic of this talk. So let's dive right in. How do we design recommender systems at Google for the scales we have? So before, let's pause for a little bit, and if we want to summarize, what happened to the world of IT over the past 30, 40 years, there were different waves. The first wave was definitely led by hardware, and companies like Intel and AMD were really the companies, and IBM were the companies driving the industry. But with Microsoft, things changed, and basically, driving force of the IT companies were driven by software. And from the late 1990s, I would say, to the early 2000s, the king was data. So the companies who had the most data were really, deciding the rules of the games, pretty much. And that was indeed Yahoo, Microsoft, Google, Amazon. And as you know, over the past 10 years, machine learning has been flourishing a lot. And together with data, because this data is the fuel for machine learning, and together with good hardware and good software, the companies that have all these things, hardware, software, data, are the ones that are able to push the envelope in machine learning. And so I feel very fortunate that I'm at Google today, because we are very much in this situation. So recommender systems, everybody knows what they are. They are totally ubiquitous. They are everywhere. Here are listed just a few. I apologize for having omitted the logos of all the non-Google companies, but these slides have been vetted by the Google lawyers, and I don't have copyrights to put there the Netflix logo or the Amazon logo, apparently. So I had to take out all these logos. But anybody have a lot of experience with recommender systems through many of these companies. And in India, you have many equivalent of those American companies, and you can relate to that as well. And I think all of us have our personal stories. I think the company that really put recommender systems on the map is certainly Amazon. I remember myself maybe 20 years ago, it must have been in 1998, 99, when Amazon was still that company selling only books and CDs. I was amazed, right? When you go to Amazon and you look for this music or this book, and you have this everybody that looked at this item already also shopped for this item or this item. I discovered a whole new branch of blues from Mali in Africa that I would never have known if not for the amazing recommender system that Amazon had at that time for music. So, I mean, they are really a key component of our life, and they are in constant evolution and improvement. And I will finish this talk by giving you an idea of how I see the future of recommender systems. Okay. So at Google, we have recommender systems everywhere. I mean, I mentioned that I'm in a research group, so we work on the core of the recommender systems algorithms, but we are also collaborating with many product groups that use recommender systems. So here I just, as an example, show the Play Store on Android, right? When you go to the Play Store, you have apps that are recommended, right? Those apps are typically not chosen at random. They are based on everything that Google knows about you, because we would like to maximize the chances that you are going to click, install, and play with, interact with the next app, right? So that's part of our business. But the biggest of our internal customer for recommender systems is definitely YouTube. So I put here an example of YouTube have two main fundamental recommender systems. One is what we call the homepage YouTube. So when you come for the first time on youtube.com, you have videos that are recommended there. If you're logged into your Google account, these videos will be tailored to you. If you come out of an incognito window when you're not logged in, those recommendations will be the same for everybody, and they will be like the most trending videos at the top, of course. And then when you start watching a video, we have the watch next recommenders, which is the one that is depicted here, right? On the right hand side, you have a list of videos that we think you might want to watch next. So these videos are tailored to you if you're logged in, again, if you are signed in to your Google account, and they are also depending on the current video that you are watching right now. So this is a very critical task, because, of course, we want people to spend as much time as possible on the product, on YouTube. So how do we go about selecting videos that will maximize the chances that you stay on YouTube for as long as possible? Just to put things in perspective, there is about, at any time, 2 billion videos we could choose, this maybe 20 videos that we show there from. So that's a lot of videos just to parse and decide which one are going to be the best suited to be the one you want to watch next. And then in which order do we put these? There is 20 videos, and there is only, like here you see on a normal screen, typically 8 or 7 or 9 videos that are above the fold. Very rarely people scroll below the fold. So how do we select the rank of these videos? And in particular, the top one, the one that is above this little line here, is the one that will play automatically if you don't do anything. So we want to make sure that this video has a good chance to entertain you further, because so you will, let YouTube keep playing from video to video, and you will spend a lot of time on YouTube. So here I put this chart, that's supposed to represent a histogram, and this is just to make a point that YouTube videos, if you rank them by popularity, they follow a power law, just like what I'm trying to illustrate here, meaning there are some extremely popular videos. As you know, there are videos that have hundreds of millions of views. And of course, there is a very long tail of, the video that your aunt or your cousin or your sister uploaded, right? So, those videos are very rarely watched. So in recommender systems, there is a very delicate trade-off here to make, right? We could recommend the head videos to everybody. Like everybody will recommend the Gangnam Style or, this extremely popular video. We will have probably a lot of clicks, and, for a while, people will be delighted, but then, they will be not enthralled by the product, because they would not, learn new things, discover new things. While if we play a little bit more risky, and instead of recommending what we call head videos, we would recommend torso or tail videos. But if we manage to find tail videos that are really of interest to you, then you're like, wow, really, I'm discovering niche things that I didn't know about, and I really enjoy that. So, it's a challenge of exploration, exploitation, taking risk, or playing safe. And our algorithms typically have to address that. Okay, so it's not only the recommender systems can be used as general classifiers. It's not just for recommending videos or books or movies. Typically, for example, now that you have this auto reply in Gmail, you can imagine that once you receive an email and you have this selection of possible replies, this is also a sort of a recommender system, right? Based on not a user or a video, but a user and a text of an email. Here, the system has to choose out of million possibilities to show like 3 candidates, but they are the 3 most likely that will be used by the user, by the reader of this email in this case, to as a reply for this email. So you have to think of this recommender system not just as recommending items to users, but they are really used as general tools in machine learning, what we call multi-label classification, when each example has to be assigned some labels and can have multi-labels attached to it. Examples can be users and the labels are videos, or they can be users and the label are apps in the App Store, or here they can be email and the labels are possible replies. Okay. So the outline of the talk, I'm going to describe a little bit more formally what a recommender system is. And then I will go over very briefly the taxonomy of all possible algorithms that we can use for recommender systems. Then I will describe, I will focus out of this taxonomy on 2 models in particular. They are based on matrix factorization, the first one, and the other one use a deep neural network. I will describe those in more detail because these are the ones that can really scale to our scales. Then I will give you an idea on how we serve these models. And finally, I will mention what are the challenges that recommender systems faces, draw some conclusion, and at the end, I will, I didn't put here on the outline, but I will finish by telling you where I see the future going for these recommender systems. And also after that, I will mention what are, the disciplines that you should study if you are interested in working on recommender systems, and not just using some recommender systems algorithms to apply to specific problems, but really developing new algorithms for recommender systems. Okay, let's dive right in. So, little bit of math notation, but nothing too fancy. So, how do we define a recommender system problem? So basically, we have a set of users that will be indexed always by I and going from 1 to M for users, and a set of items that will be indexed typically by J, and that will go from 1 to N. So M, the number of users, N, the number of items. And here, I just should reiterate what I said before. I'm going to use the word user and the word items just to make things very specific. But you have to think that behind this user, these items, it can be anything, right? The user could be an email, or the user could be a video, that the video you're currently watching, or the user could be a sequence of videos that, if you are not signed in, for example, in YouTube, and you are watching video 1, video 2, video 3, video 4, we don't know anything about you but the sequence of the last X videos that you saw. And so based on that, we would like to make a recommendation. So the item will be, of course, a video, because this is what we recommend. But the user will be just the sequence of videos we saw in the past. So behind the word user, you have to imagine that it is anything that all the information that we have to the entity we want to recommend items to. And behind the word item is the kind of thing we're recommending. It can be books, movies, replies to emails, etc. Okay, so given that a set of users and a set of items, the goal of a recommender systems is, find item J that the user I will like. Okay, so that's as simple as that. So what is the data that recommender systems are built on top, right? So an obvious type of data is the item metadata. So if items, for example, are videos, it could be the audio soundtrack of the video, features extracted from the audio soundtrack, or features extracted by the sequence of images in the videos. Or it could be keywords that are provided by the creator of the video, or description of the video, or it could be the identity of the author of the video, or the artist, or the actor, director, if these are movies, for example, etc. I mean, you get the idea, right? These are all sorts of features that describe each item that have to be recommended. So this is a good source of information, okay? And the other part of the information that we can use, in some cases, if we have it, is user metadata. So if a user is a user, like I said, it could be anything, but in the case it is a user, metadata for user could be demographic information, right? If we know age, gender, education, income, etc. of the user, maybe we can use that if we don't violate any, user privacy, of course. It could be geographic information if we know where the user lives, or, is it urban, is it rural, which country is the user living in, or it could be the language the user speaks, or, as I said before, the past activity, if we just have, a sequence of video or a sequence of books that the user has uploaded from the system. This is the second piece of information, and you can see how this can be really useful to make good recommendation of items to user. And the third piece of information is user-item interaction. So in this online system, oftentimes, in some cases, we don't have even any item metadata or user metadata at all. We just have the item is just an ID, opaque ID. The user is just, again, an ID, like a cookie. And the only thing we know is, oh, this particular user has, consumed item A, item C, item X, and that other user has consumed item B, item C, item, etc. Right? We know the interaction between many, many, many users for which we might not know anything, and many, many, many items for which we might not know anything as well. So this is what we call the collaborative filtering information. And this comes in two different flavors, right? It can be either explicit. Let's say when you go to a system like Netflix and you give stars after or before watching a movie, right? You can give 1 star, 2 stars, 3 stars, up to 5 stars. So this is an explicit rating. So we have not only a link between a particular user and a particular item, but we have also a value assigned to it. It could be thumb up, thumb down that you do on YouTube or on some music streaming system, etc. It could be simply a click. But in many cases, we only have implicit information, right? We just know, oh, this user watched this video. Maybe we can also compute how long the user watched the video. What is the percentage of the time of the video that got watched, right, before the user turned off? And this is what we call the implicit information. So, each of these three pieces of information, the item metadata, user metadata, and user item interaction, are important in their own right. But we tend to think, at least in the online world, right, where we build recommender systems online, that this third brick here, the collaborative filtering information, is the most essential and critical to build these large-scale recommender systems. First of all, because we always have it in one form or another, but also because, yeah, it's massive, typically, the amount of information we have there. But at the same time, you have to keep in mind that it is very partial, in the sense that if you just consider the entire matrix of a user item, right, it's a very tiny, tiny fraction of this matrix that we have ever observed, right? If you go to Amazon, there is probably 100 million items that you can shop on Amazon, right? And each user has maybe in a lifetime bought 50, 100 items out of 100 million, right? So it's 1 in a million. So the density of this matrix, the part that we have observed, is extremely, extremely small, right? So much, much smaller than the total number of users times the total number of items, obviously. So a very important question is, how do we handle all the unobserved interaction, right? If a user has not consumed a particular item, if a user has not watched a video on YouTube, if a user has not downloaded a specific book, does it mean that the user doesn't like this book? Or does it mean that the user just doesn't know about this video and maybe the user would have loved it, right? So this information has to be used somehow. And it's very critical to building good systems to use it the right way. Okay. So here I'm going to try to give you, a summary of all the different kind of algorithms we can build to build the recommender systems based on the different kind of information we have. First, if we are using metadata, we build systems that are known as content-based systems, right? And if we use, the item metadata, we can build item similarity, right? Between each item, we can build a similarity function. If they share a lot of similar information, they're of the same language, they're on the same topic, etc., these two videos, then they are very similar. If they are of different topic, different language, etc., then they are very dissimilar. And once we have this similarity function between items, we have an easy way to making a recommender systems, right? If a user is there and we know a set of items that the user has consumed in the past, we can find items that are very similar to the items that the user already consumed and recommend those, right? Symmetrically, if we have, instead of item metadata, if we have user metadata, we can use them to build a user similarity function, right? And two users will be similar if they are from the same region, with similar demographic and geographic, they speak the same language, etc., then they are very similar. If in the opposite case, they are very dissimilar. And based on this information, if we have, again, a little bit of user-item interaction, we can build a recommender system by the following way, right? When a user comes, we see all the users that are more similar to this user. We look at all the items that these very similar user to user X have consumed. And out of those, we look at those that are the most frequently occurring among the similar user than user X. And we look at those that user X has not yet consumed, and we can recommend those. Very simple. Now, if we have both, item metadata and user metadata, we can combine both these similarity measures on items and users to do things even more, accurate, I would say. Now, on another hand, if we want to tap into that third brick of information I was mentioning before, which is the collaborative filtering information. So we actually don't need anything else. In some cases, as I mentioned, we have only that. And there we build systems that are known as collaborative filtering systems, right? And that's what we will dive into more. We call them, at the simplest level, if we have no other information than just the collaborative filtering information, we will build factor model, and I will give you a good idea of what those are. And finally, if we want to, if we have everything, we have a good amount of collaborative filtering information, but also item metadata and user metadata, we can build a more rich system that tap into everything. And we will also talk a little bit about those. So I will, in the rest of the presentation, I will not cover, these content-based systems, because in particular, they don't scale very well, right? All I was mentioning here is building a similarity measure between items based on the item features, or a similarity measure between users based on user features. And as you can imagine, these measures will be typically quadratic into the number of items or the number of users. And when you have a billion items, a billion square is a very, very large number, even with today's computers. So it's very hard to start deciding for every pair of items how similar these two are. There would be other ways around it, but we typically go directly to this more complex model that use all the three sources of information. Okay. So let's talk about this collaborative filtering and this a little bit more. So to go a little bit towards formalization of the problem, right? If we have a little bit of user item information, we can call this a utility function. We know how what's the utility for this blue user, this Saturday Night Live video here, for example. It's a utility 2. And we know that for this green user, that karaoke in the car with Adele is of utility 1. So typically, maybe this green user doesn't like much entertainment videos. So we have this very partial information. As I was mentioning before, we know only a tiny little bit of this entire user item matrix. So we have, we know this matrix A for, only a very small portion of the entire m times n. And we are going to talk about matrix factorization. So how do we, okay, maybe going back here, the aim of the game is to then predict values for the entire matrix, basically, right? Once you want to make a good recommendation for the blue user based on the fact that he has a utility of 2 with this video, a utility of 1 with this video, and utility of 2 with this video, we would like to know how likely is he or she to like this video and this video and this video, and then pick the highest one, right? Rank all these videos in decreasing order based on that, right? So in simple words, we would like to complete this matrix, this very, very partial matrix, right? So given, again, a very partial matrix, we would like to find a matrix A that is full, right? And that matrix A, we would like it to match, so this Aij, here, remember, I is an index for the user, J is an index for an item. So over all the user item pairs that we have observed, for which we have a utility, so this omega here will be the set of all the observations, right? Basically the set of all the white entries in this matrix, this very partial matrix. So for each one of these observations, we would like that this matrix A star here is as close to the observation we have, right? So we want to pick a matrix A star that is full, completely defined, and that matches as closely to the partial matrix A that we have on all of these observations. And again, I cannot stress enough, remember that these partial observations are very, very partial. I mean, it's a very small set. So Obviously, we cannot do this totally freely, right? Because there is way too many coefficients to choose for this matrix A star, right? If we can choose it arbitrarily, well, nothing prevents us to choose them all 0, for example, which will be of no real value. So we have to impose some constraints on the problem. So, and the most popular constraints that we are going to work with, we are going to assume that A is a matrix of low rank. So now I'm assuming that all of you have done some linear algebra, but maybe you need to be reminded what a low rank matrix is. So because this is key for this understanding, so I'm going to spend another 2 minutes to remind you what a low rank matrix is. And there are many ways to define low rank matrices. The one I'm going to show you now is probably one you have never seen before. Believe me, it's totally equivalent to the other definitions. And this is the one that makes the most sense in the context of what we are doing. So if you have an arbitrary matrix m times n here, like our matrix, right? We will say that if it can be written as the product of two matrices, like one tall skinny matrix n times k, I assume that k is not as big as m, times another wide flat matrix n times k, k times n. So if I can find two such matrices such that that matrix product of these two is that very big matrix n times n, then by definition, we know that the rank of this big matrix is at most k. So, you can try to find the smallest, the skinniest tall matrix here and the flattest wide matrix here such that this can work. And then this will give you the rank of the matrix, the big matrix m times n. Just to give you an example in numbers, this 2 by 3 matrix here, let's say we have only 2 users and 3 items, is actually of rank 1 because, I could write this as, this little vector here, 1, 2, times this vector 2, 5, 3. You can check that, there is this structure in this matrix. So a low rank matrix is a matrix that has a lot of structure, right? And why is it very critical for us to use this kind of constraint on our matrix is because it simplifies the computation a lot, right? The computation and the memory. So remember, m times n could be enormous. We never want to have to compute anything in the complexity of m times n or to store, even worse, right, this amount of memory, because typically we will have hundreds of millions of users, so m, and billions of items. So you never want to go towards the product of these two things. So if you can rewrite this as the product of these two matrices, and you will, of course, never compute explicitly the product matrix. So the complexity, for example, for storing of these two matrices is just n times k plus n times k, which is m plus n times k. So you have replaced this product of these two enormous values here by a sum, which is way more manageable. N times k, in practice, we will use k being 100, 200, 500 at most. So it sounds big, but it's actually very, very tiny comparing to n and m. Okay, so one very simple illustration as of why it makes sense to use low-rank matrices for our case. So again, imagine that you have this very partial matrix where you know only the white cells of this matrix here, and you want to infer all the rest. So one intuitive thing to say is to say, okay, let's give a prior for each of these users, how likely they are to find an item useful, the utility of an item. And same thing for each item, we'll give a prior value. How likely is this item to be found useful by any user, right? And so this will be a vector, and this is a vector. So the product of these two vectors is now a rank 1 matrix, just like that one here, right? So with this rank 1 matrix, we already get something, right? Maybe we can find these two vectors such that when we multiply, this vector by this vector, we get this full matrix here that I wrote down here for you. And maybe it matches exactly the matrix A, the partial matrix A that is given to us on these white squares. But maybe not. Of course, it's probably going to be very hard to find such a small rank matrix that match exactly. So we can find something that match as closely as possible. But this will be a little limitative, because here we're really trying to say, okay, every user should be ranked on a linear scale, a single line, assigned a single number, basically, and every item will be assigned a single number, and basically the product between the user number and the item number will directly give us how likely this user liked this item. So this is probably very hard to achieve. As you can imagine, if you have videos, right, you have users that like maybe action movies, but also like movies in English, and also like movies from the 70s, right? So there are many, many dimensions. It's going to be hard to solve such a problem on a single dimension. No problem. We can just crank it up and go to rank 2 matrices, maybe. So as a simple fact, what I didn't illustrate on the example before, a rank K matrix can always be written as a sum of K rank 1 matrices. So this is illustrated here. Again, we have this very partial matrix at the beginning that has only the white square available, and we want to complete it. And for that, instead of assigning only a single number to each user and a single number to each item, we'll assign 2 numbers, right? Maybe 2, 1 here for the green user, and 0, 2 here for that Saturday Night Live video. And then the utility function between the green user and this Saturday Night Live video will be determined by the dot product, the scalar product between these 2 numbers and these 2 numbers, which is 2 times 0 plus 1 times 2, which is 2. And between the green user and that Adele video, that will be 2 times 1, which is 2, plus 1 times 2, which is 2, 2 plus 2, 4. So you realize that here we can build a little bit more complex matrices. Still low rank, but rank 2 instead of rank 1, right? And in practice, so here we are looking for, 2 matrices U, that matrix that represent the users, right, representing each user with k scalar values, and a matrix V that represent the item, again with k scalar values, and the matrix, the prediction matrix that we are building to associate a value for each user item pairs now for the full matrix will be just given by U transpose T. Again, remember, we never calculate this full matrix. We never calculate anything that is m times n. But when a user comes and we want to know how likely is he or she to like this item, this particular item, then for this pair only, we can find out through this matrix what's the utility for this user and this item. Okay, so in a sense, what do we do when we go to rank 2 here? Instead of projecting the users and items on a single line, it's like we're projecting them on a plane, a 2-dimensional plane. And maybe we could even, in some cases, go further and associate some semantic values to each of these 2 dimensions. For example, in this simple, video examples that I totally constructed artificially, we can imagine that one dimension is child friendliness. Here, Thomas the Train is the most child-friendly YouTube video in my toy example. And here, it's entertainment value. So maybe Saturday Night Live, John Oliver, and, karaoke in a car are very entertaining. But child-friendliness, for these 2, not so much. These are really adult things. So the idea, phrased differently, right, is we choose an Euclidean space, a k-dimensional space, right, continuous space, and we try to project every user as a point in this k-dimensional space and every item as a point in this k-dimensional space in such a way that the dot product, the scalar product between that user point and that item point gives a value that is as close to the utility for this user and this item. So based on a very partial knowledge of these utilities, we are going to solve this problem, project all the points in all the user point and all the items as points in this space, such that this is realized, based on the partial information we have. And what else can I say about this? This has a lot of good properties. One of them is that, in this embedding space, this k-dimensional embedding space, we are tapping here into transitivity information, right? If for a particular user U, we have observed that this user U likes video A, video B, and video C, right? So this user U will end up close to the videos A, B, and C, hopefully, in this k-dimensional embedding space. Then maybe this user U, this user U has a lot of videos in common, likes a lot of videos in common with other users, V, X, and Z. And these other users are themselves close to some videos that this user U has not viewed. But since this user U has a lot of common videos that he likes with these other users, the point of this user U will be also close to the points of these other users, V, W, and X. And those users themselves are close to the video they like. So you can see how by transitivity, the videos that we are going to find being close to this user U, but we don't know, it's not part of the matrix we have observed, are likely of interest to this user U by transitivity. So that's the key property that this low rank matrix decomposition here is basically tapping into. I hope all this makes sense. So to be a little bit more specific on the problem we're trying to optimize, once again, we have very partial information, this matrix A in the M times N space. We know only few values of it, right? Defined by this set omega, only for the ij pairs that are in the set omega. We have observed an aij, and we would like to find a matrix U and a matrix V such that, so this matrix here I've chosen to represent it as the column vectors of this matrix are these vectors for each user U. So the column of the eth column of this matrix U will be the little vector of size k that represents this user I. And same thing for the item j, right? The jth column of this matrix will be the little k-sized vector that represents the item j. And the dot product between these two things will tell us what's the utility of item j for user I. So the problem we're trying to solve again is find the user matrix U and the item matrix V such that for all the observed values, these utilities, predicted utilities, I should say, are as close to the observed utilities as possible. Okay? I hope this will make sense. So now, as I said before, a key information is a key trick to build good recommender systems is how do we use the unobserved part. So from the 2008, I think this paper it was a paper as part of the Netflix prize, we know that it's very important to also use the unobserved part of the matrix. And in particular, the simplest thing we can do is to just assign a prior to everything we have not seen, maybe 0. I don't know what the stars are, maybe 2. If it is, let's say, Netflix and all the stars are between 1 and 5, and maybe the average number of stars is 3 or 4, maybe we want to pick this prior being 2 or something lower than the average, right? Because you have to assume that if I've not watched a particular Netflix movie, it's maybe that I don't know about it, but also maybe that I'm not particularly attracted to this movie. Maybe this movie is not in the language that I speak, etc. So it should probably be a little lower than the global average number of stars that users give to Netflix movies. Anyway, so let's pick a prior value, for example, here 0. And now the problem that we are going to solve is a little different in this way. So same thing, we have given a matrix A, which is a very partial information about the all utilities between users and items. And we want to find this matrix U and V as before, where we minimize this. This is the observed part. This is the exact same term as we had before. So for each observed user item pair interactions, we want that the predicted utility between a user I and an item j is as close to the observation. But we also add this part, which means, for every non-observed user item pairs, we would like that the predicted utility for the non-observed pair is as close to that global prior that we chose here. And also, like it is customary in machine learning, right, we would like to also minimize the complexity of the model. This is to control over-prediction. So we add a regularization term where we say, okay, these matrices have to be as simple as possible. We don't want the values of these vectors here to get too big. So this is the Frobenius norm of the matrix, which just means that basically the sum of all the components of these vectors squared should be as small as possible. And here we have, those parameters gamma and beta, which kind of, weight these three different components in this global loss. But basically, this is what we are trying to minimize. So to do that, there are many different techniques. So I'm not going to go into detail here. Some of you might be familiar with this technique, some won't. Let's just say that, the basic one is stochastic gradient descent. We can compute the gradient of this loss function here. This is a loss function. And at each step, we pick some users' item pairs that we have observed, and we compute the gradient, and we modify the matrix U and the matrix V, which are the parameters of the model we're trying to learn. We modify them to decrease that loss a little bit based on this observation, and we repeat. Coordinate descent is another technique that is similar to stochastic gradient descent with some nuances. Or we can use weighted alternating least square. So this is something I can explain very easily. So this problem here is known as a biconvex problem. It's unfortunately not convex, it's biconvex. But what it means is that if, for example, we fix V, for example, now we decide, okay, we have some V, the matrix V has some values, and we don't change them, then finding U that minimize this entire loss here for this fixed V is actually an easy problem. We can work out, an analytic solution for it, and we can solve it efficiently. So what alternating a least square does is that it does that in alternance. First, we pick U and V at random, very, very small values. Then we fix V, we find the best U for this fixed V. Then we fix U, we find the best V for this fixed U. And we go like this back and forth. And in practice, you have to do this 20 times, and the system converges quite rapidly to a good solution. We know it's not necessarily the optimal solution because this is a non-convex problem and it's extremely hard to solve optimally. But in practice, it works very well. Here I mentioned, this loss function, which is known as the squared error, right? Because we are squaring the error between the predicted value for the utility of a pair ij and the observed value. But depending on the problem you have at hand, you can use other loss functions. You can use a logistic loss. For example, if the problem you have is to predict, the likelihood of a click, which is something that can happen or not, but it's a binary event, right? And you want to predict the probability of this binary event. Or you can use a softmax cross entropy, which is used in the case of multi-class classification. Like, when you have a user, that this user like many items, you would like to model this as a multi-class classification, right? This user has these labels or these items, and you want to find eventually other labels that suit this user well. In this case, we have another loss function, which is called softmax cross entropy. I'm not going into details. So finally, the last component of this talk I was promising you I will go over is this DNN model. So what do we do when we have, also metadata about users and items or both, right? And we would like to build upon that idea of factor models, because this is the one that scales the best to the scales we have at Google. So it's actually very simple. And just on 2 slides, I will give you an idea. So far what we were doing, we were building a function f such that for each user ID I, it will give us a user vector of dimension k. And we'll have this for all the i's from 1 to m, right? So this could be just a mapping. Our matrix U basically can be seen as a function that maps an index into a vector. Same thing on the item side. Our matrix V can be seen as a function, let's say H, that map an item index J to a vector of dimension K, the Vj that we talked about. So now if we have metadata for this user I or metadata for this user J, the only thing we need is to enrich this function and say, okay, now the function f that will give us a vector of dimension k for this user I will not only be based on the simple ID I, but also on all the metadata we have about this user I, being the language, the demographic, the geographic information, etc., whatever we have. Same thing for on the item side, right? And this basically, it's very key because we can solve the cold start problem. What we call the cold start problem is, for example, in YouTube, right? How do you recommend videos that were just uploaded, right? YouTube has, the latest number I heard is there is about 400 hours of YouTube videos that are uploaded every minute, right? It is a staggering number. So it means there is a lot of videos out there that are very new. And a good recommender system should be able to quickly recommend the new videos, right? If something is getting hot very quickly, you don't want to have to wait a month to have seen many users liking or watching this video before finding out, oh, actually this video is good for those users, let's recommend it. So you would like to be able to do it as soon as possible. So this is done using metadata, right? So this function H here will be able to give us some VJ, even if we don't have any interaction between any user in this video, but just based on the metadata. So how do we build these 2 functions? So that's I'm going to summarize this just with this simple illustration. We build what we call a 2-tower model. It's also called sometimes a Siamese model. So it's a neural network. It's actually 2 neural networks. And just to put things in perspective, what we were saying so far in the matrix factorization case, we can see this as a very simple 2-tower model where the 2 towers are shallow, right? At the input here, we just set the ID. So for example, for a particular user I, it will be encoded here at the input layer as a bunch of zeros, 1, 1 at the eth position, and then a bunch of zeros. Then we have a fully connected layer here to this layer that is of dimension k. And basically what the product here does is that it will put on the layer here of dimension k the vector ui, right? Same thing on this side, we'll get vj here, and then we do a dot product ui vj to get the predicted utility for user I and item j. So now if we have a lot more data than just the ID here, we just throw in like a big neural network that encode here everything, maybe the ID if we have it, maybe we can encode the language that the user speaks, the geo, the demo, everything we have, right? Same thing on that side, and we can build a complex deep neural network here that will map all this information about the user into a vector of dimension k, which will be our UI. Same thing on this side. It will map everything we know about the item into a vector of dimension k, which will be our vj, and at the end, we just do the simple dot product like we did. So I hope this all makes sense. That should be, straightforward to understand, at least at a high level. And then we train this model just with stochastic gradient descent, like before. We look at a bunch of interactions that we have seen between users and items, and we back propagate through both this neural network here, the information, the gradients, to update the parameters of this model until it converges towards something that is good enough. Okay, just one more slide about the technicalities here. How do we serve these models? I keep telling you that this factor model are easy to serve. Well, the way it works is at our scale, right? How do you find in like milliseconds out of 2 billion videos, which are the videos that a particular user will like? So first you train the model, like I said, the kind of models we have, right? You find this matrix U and matrix V, or this entire neural network for the user side and neural network for the item side. You organize this matrix U and matrix V, actually the matrix V itself, the VJs itself, you organize in such a way that we can run then a maximum inner product search very efficiently. So there are sublinear, actually logarithmic algorithms that can find, given a point in an Euclidean space, find, let's say, the top 20 closest points. If we have organized these points before, the top 20 closest points, even if we have a billion of them. And then you store all these organized VJs on disk. And now this is all done in batch, right? You have the time to do that, etc. Now at serve time, when a user I comes, you compute the vector UI for this user, right? If you have the deep tower case, you just feed forward the features that you know about this user I through the left tower to get the vector UI at the top of the left tower. And then you run your maximum inner product search algorithm against this database to find the VJs that are the closest to this UI, as simple as that. And then you serve the items that correspond to these Js. Okay, so that was, in a nutshell, what scalable recommender systems are. So now 2 words on. So actually, I see that I'm running short on time. So let me go straight to the conclusions. So I've reminded you how important recommender systems are in our real life. Our mature technology today, we can handle problems where the number of users and the number of items are, in the 10 millions to a billion, typically. It's a balancing act between being safe and risky. As I said at the beginning, right? We can recommend very popular videos, and most likely the user will click on them and enjoy them, but maybe on the long term, they will not be delighted by the product. And yeah, there is a lot of feature engineering that happens behind the scene that I brushed over. So where do I see the future of recommender systems? Maybe that's more interesting. So first of all, I think we have pretty much nailed down the best strategy to make sure that you are going to click on the next YouTube video, let's say, to take the YouTube example. But how about trying to please you, to delight you on the long term, right? Making sure that you're not going to watch a video for 2 minutes and then say, oh yeah, that was just such a waste of time. I mean, I laughed, but funny cat videos, right? Everybody loved funny cat videos. But how do you feel after having spent half an hour watching funny cat videos? You don't feel really, improved as a human being, right? While if we are able to show you a video about building something that you are actually interested in, but you never thought of inquiring on YouTube, and then you are discovering a totally new field, and for the next 2 hours or 3 weeks, you're watching several videos of the same kind and make you discover something new, learn something new, learn a new trade, that will be really a much better experience. So that's what we're heading to. We're using, advanced machine learning techniques like reinforcement learning to try to delight the user on the long term instead of just, watching the next funny cat video. And the next big trend is, as you heard in other talks in this series organized by Prita, everything is becoming conversational. So to be fair, right, the user interfaces that we are using in our recommender systems is still very outdated. It's just a list of things, and we have to go down the list and choose a visual list of things and choose down that list. Being music recommender systems, YouTube, anything, right? It's Netflix, all operates like that. So the future, as you can see with Alexa and Google Home devices, it's going to be much more conversational. So how do we build conversational recommender systems? Let's imagine the following scenario. You come in your home and you would like to, be listening to some relaxing music, and you say, "Hey Google, play some classic rock, please." And Google starts by picking one of the hits from Queens and play "We Will Rock You." And you're tired, you had a long day at work, your head is hurting, you're like, "Yeah, classic rock, I didn't mean that kind of loud. So how about you play something more mellow, please," you say to your system. And then the system goes on and, start playing Hotel California, much more mellow, still, classic rock kind of music. But you felt like something, this is a little outdated. And you were there with your friend and you don't want to look like an old grandpa. And you are saying, "Oh, I meant to stop you." And you are saying, "Hey, Google, play something more recent, please. Stick to this century, for example." And then, Google suggests something else and, go to One Republic and play Counting Stars and so on. You can imagine, how complex this is. So this brings in, okay, I meant to stop you. This brings in a whole different set of, AI components, right? You have to do speech recognition. You have to do, language understanding. You have to keep context of, what the user is in the mood for, and so on. So, but this is where I see recommender system being in 5 years from now, maybe. So to conclude, if you are really delighted by machine learning in general and you want to make it part of your career, and you want to know what are the fields that you have to focus on to be a good machine learning scientist in the future, I would say, my background is in math and computer science. Obviously, both components are very important. But I tend to say, every time I get this question, focus on math. Computer science is easy. Computer science, first of all, it's changing very rapidly, right? As I said at the beginning, I'm quite old. I did my PhD in the early 1990s. None of the programming languages I use for my PhD are still around. They have disappeared, right? It was Pascal, it was Ada, Modula. Nobody knows about these languages anymore. Then came C++, then came Java, then came Python, and so on, right? We don't know what will be the languages in 10 years. So don't spend too much time becoming an expert in Java or something like that. If you want to focus on computer science, look at becoming very knowledgeable in data structures and algorithms. Those things are, always going to be very important. But my point is that it's very easy to pick up computer science skills, even when you are aging. Mathematics skills, when you start to get in your 40s, in your 50s, it's much harder to pick up. Plus, these are forever things, right? Everything that we are using in linear algebra today was discovered, in the 19th century at the latest, right? So the three components that are fundamental to machine learning, I would say, is linear. First of all, statistics, right? Learn statistics inside out. That's key, right? To be a good data scientist. Focus on linear algebra. As I told you, right? All these machine learning approaches, this is not just recommender systems. It's all about projecting points in spaces and then doing, matrix operations in these spaces. So linear algebra, all my colleagues that are like superstar in linear algebra, they are heads and shoulders above everybody else. And of course, optimization. As I was mentioning, you always set up your problem as a loss function that you want to minimize. And if you are an expert in optimization, very sophisticated optimization techniques, you are bound to help the field make jumps forward. Okay, so I think this concludes my presentation. And Prita, I'm back to you.
Wonderful.
I went a little over time.
No, that's okay. I do have a question, though.
Yes, tell me.
So you gave us a very good overview of some of the skills that are needed to make an impact in the field. What sort of advice, if you have any, for students starting out in this field? What sort of, do you think they should be focusing on math, or do you have any advice for them?
Yeah, definitely. Like to my last comment, right? Focus on math. Of course, use computer science, but don't make computer science the subject of your study. So computer science is just a tool, and those tools are changing rapidly. You know, learn your linear algebra inside out. You know, learn statistics, learn probability, of course, calculus. Although, I mean, calculus is even more fundamental, right? In my picture, probably it would have been the stairs at the bottom of this edifice, right? And optimization. So yeah, focus on those, get really very strong expertise in those fields of mathematics. I have to tell you, you know, I probably never...
Nick,
Yes, tell
turn
me.
off your screen share so we can see you.
Oh, I will turn off my screen share. Yes. Okay, let me do that. Why? Yes.
There you are. All right, just continue.
Yes. Is it off?
Yes, it's good.
Okay.
Yeah.
Yes. Yes. Focus on this field of mathematics. I think that's what will arm you the best. You know, then you will join a university or a company, and you will learn the tools, whether it's PyTorch or TensorFlow and all that. These are things you can learn in a week or two and become an expert in 2 months, right? While becoming an expert in you know, statistics takes years, right? So while you're at school, get your basis solid and worry about, you know, these tools, you know, once you are on the job.
Wonderful. Thank you so much. You know, it's been a very, very interesting talk, and I think your advice is right on. So we all thank you, and once again, thanks a lot, Nick, and good evening.
Yes, thank you, Prita, for the opportunity. It was a pleasure.
Sure. Bye-bye.
Good evening, everybody. Bye.